So let's continue with 8.2. So if we were to give you this problem, so looking at this thing here, as you can see, is so wordy, right? It's so wordy in terms of the problem is all wording. So one thing I want to point out is if you were to have this problem, how would we go and detect or extract out the information that we needed? So this is what we have is a large comedy. At the large comedy, the attitude of the worker are regularly measured with a standardized test. The score on the test range from 0 to 100, with higher score indicate greater satisfaction with their job. The mean score overall of the company employee was 74, with the standard deviation of sigma equal to 8. Some time ago, the company adopted a policy of telecommuting. Under the policy, workers spend 1 day a week at home. After the policy in place, sometime later, the random of 80 workers were given the test to see whether the mean level of satisfaction have changed since the policy was in effect. So the sample mean was 76. Assume the standardization is still sigma equal 8. So again, based up all that, this is what they want you to do is, can you conclude that the mean level of satisfaction is different since the policy change at the level alpha equal to 0.5. So if you look at this thing here, and one thing I told my student, or one thing I tell you guys is, if you in doubt, just go in and just circle all the number that you have, because statistic, that's what we're looking for, right? Circle, which is, again, we know that we have 0 to 100, which is, hopefully you guys see that that is a useless number. And again, we have 74, we have a sigma of equal to 8, and we have the 80 worker, and we have this number here, and this number is the same as the other one. But again, if you in doubt, if you don't know where to start the problem, just go in and identify all your number, right? Just block out all the information or the backstory. So looking at this thing here, why do I say that 0 to 100 is useless? Because again, looking at this thing here, this is just an information, right? This is just a category in terms that we don't really need that for our test. Right. So looking at this thing here, how do we know which one to use, or what do we have? Well, clearly, hopefully you guys see that the easiest one to see is the N, which is the number of worker we have, which is, hopefully you guys see that we have a total of 80 worker, right? How many worker do we sample, which is the sample of 80, which is the N is 80. And hopefully you guys see that clearly they say sample mean. What does the sample mean? Because based on this 80, this is the mean of this 80 worker, which is sample mean is X bar, right? And again, the sigma, which is, again, it's the same sigma, which is sigma is equal to 8, which is, reminder, the sigma is your population standard deviation. So in this case, this is what we have here is the sigma. So now the only thing, well, the other obvious one is probably you will see that the alpha is equal to 0.05. So those are the obvious number, right? The only thing that left out that we haven't seen is the 74, which a lot of students probably say, wait, how do we know what number, what is the specific number that we use to test or we try to compute? So the first thing I tell my student, as you will see later on, that most of the time, when you read this question that they ask you, can we conclude, or can we state, or can we verify, can we conclude that the mean level of satisfaction is different? So different from what? Different from, again, do you agree originally, what is my mean? My mean is 74, which is, that is the original mean, which is basically this thing here is, we try to see if the level is different from the 74, from the previous since the policy change, right? So looking at this item here, so one thing, the hardest part is to know which specific value are we try to compute, right? We try to see if the level is different from the 7.4, which is the 7.4 is the original mean, right? The mean that we have. And now we want to test to see if it's different from this particular mean. Okay, so again, those are all the numbers that they have in the problem, right? Everything else is just filler, right? All of this story is just basically tell you, make sure the number is intact with the story, right? But again, that's all we need to do from this problem. All this wording, this is all we need. And hopefully you remember from yesterday, to do this hypothesis testing, the first thing we need to do is we need to have the hypothesis, right? So once we see the mu sub 0, which is the specific number we choose, and hopefully you guys see that that is the number that we will test. We want to test for the null hypothesis is the mu equal to that specific number, which is in this case 74. And if we want to, hopefully you guys see that we are not testing less than, we are not testing greater than. What are we testing? We're testing different, right? Different from, which is again, different meaning is not equal to. And this is the first time you see that if it's not equal to, reminder that this is a two-tailed test, right? So we have, again, this is my null hypothesis and my alternate hypothesis. And reminder, the alternate hypothesis is the item tell you what kind of test you have. If it's less than, if it's point to the left, it's a left tail test. If it's point to the right, it's greater than, then it's a right tail test. And in this case, it's not equal to, meaning different from the previous one, which is if it's different, then it's a two tail, which is not equal to. So now, once we have this thing here, remember, this is what we need is we need to find a critical value. And to find a critical value, we need to know the alpha, right? This is our alpha, or this is our common item we have, which is hopefully you guys see that this is what we're using, which is in this case, we have a two-tailed test. And then our level of alpha is 0.05, which is 0.05, and a two-tailed test, which is in this case, you can see that my critical value is negative 1.96 and positive 1.96, right? My alpha 0.05, a two-tailed test, I verify two-tailed because it's not equal to, and that will be my critical value. So what do we do once we have the critical value? Because the critical value tell us the boundary, right? This is what we have is I have a negative 1.96 on the left and a positive 1.96 on the right, because that's where the positive and negative come in. One positive number on the left, one positive number on the right. And because of this thing here, is tell me two things. Is tell me that I have a critical region, and the critical region is the two-tail, because I have two-tail tests. If the number fall under those two-tail, I would say that this is the reject, the H sub 0 region, right? The reject region. And if it doesn't fall under those two-tail, if it fall on the middle, then this is a fail to reject or do not reject region. So once we have this thing here, what do we do? Which is now the step 3, which is we need to construct or do the Z test, right? So our calculator can do our Z test for us. And if you use your calculator, you just need this information, which is you need an M, you need the X bar, you need the sigma, and you need a mu sub 0, your number that you want to test against, right? So looking at this thing here, if you plug it into your calculator, you should have a Z equal to 2.23 and the p-value of 0.0253. So what is the p-value? If you remember yesterday, I told you that the p-value tell us two things, right? If the p-value is bigger than the alpha, then we do not reject the H sub 0, the null hypothesis. In this case, if the p-value is smaller than alpha, then we reject the null hypothesis. That is what the p-value tell you. The p-value, if it's smaller than the alpha, we reject the hypothesis. If the p-value is bigger than alpha, then we do not reject the hypothesis, the H sub 0, right? And the other method, which is a critical value method, and hopefully you see that the critical value method is this, which is again, 2.23 is somewhere on the right of the 1.96, which is again, if it's 2.23, which is bigger than 1.96, which is fall on the right here, which is if it's fall on the right, which is fall under the reject region. And if it's under the reject region, we will reject the H sub 0. Okay, so looking at this thing here, the result we have is based on both the p-value or the z-score, we will reject H sub 0. And if you reject H sub 0, your conclusion is we do have enough evidence that the mean stretch level is different since the new policy is in place, right? So again, that's the idea, or that the process or procedure that we do in 8.2. And as you will see a little bit later, is the same procedure that we do in 8.3 and 8.4. We need to find a hypothesis, which is we state the hypothesis, we find a critical value, we find our t-test, or later t-test today. And again, in this case, we use our z-test. And then we ask ourselves, where does the z fall under, right? Is under the reject or fall under the fail to reject? And then if you reject, we have enough evidence. If we don't reject, if we do not reject, we don't have enough evidence, right? So again, first of all, question with this item here, in terms of the procedure, or in terms of the calculation, or the answer. All right. If you don't have questions, before we take a look at 8.3, there are some information that I want you to look at, or to recognize, before we take a look further in chapter 8. So the first thing is the relationship between the hypothesis testing versus the confidence interval, which is your chapter 7. The process is the same, well, not the same, right? The process, you have the test and then you reject them. But this is what they tell you is, in the testing, in the previous problem, we reject the null hypothesis, meaning we say that the mean cannot be equal to 7.4. With this level of confidence, we say that the mean won't be equal to 7.4, right? So the other way that you see that if this problem were to be in chapter 7, then we construct a 95% confidence interval. And if you construct a 95% confidence interval, because again, remember the alpha is the leftover, right? We have, again, the level of confidence, which is 95%, 1 minus 95, that's the alpha, that's the leftover, right? So looking at this thing here, if you construct a confidence level, this is what you have, is you have 74.247 less than the mu, which is the mean, less than 77, which is the interval we have is 74.24 and 77.7, which is that interval does not include the 7.4 that we have here. So as you can see, the confidence interval is just another way to prove that our hypothesis testing can be correct, right? Again, hypothesis testing is not guaranteed 100% correct. It's just say that we are confident, or we are, significantly believe that this will happen. But again, looking at this thing here, that's the relationship between a confidence interval versus hypothesis testing, is because we throw away the 7.4, is basically say that 7.4 does not belong in the interval that we have. Okay, so again, that's all in terms of the information related to confidence interval versus hypothesis testing. The other thing that I want you to see is the level of alpha, which is the probability of type 1 error. Okay, so again, I mentioned this yesterday in terms that the alpha level or the significant level of alpha is the same as the probability of type 1 error. And reminder that type 1 error is a curve when we reject the H sub 0, but H sub 0 is true, right? H sub 0 is true, but then we throw it away, right? If you remember, is we send an innocent guy to jail. That's type 1, right? And again, type 2 error is when we do not throw away H sub 0, but it's false, right? It's false, but we still cannot throw it away. That's type 2, which is set an innocent guy, or set a criminal free, right? So again, this is what we have is alpha, which is the probability of type 1 error. We want to make it as small as we can, right? And again, you say, wait a minute, type 1 error compared to type 2, type 2 is harder or damage the community more than type 1. But because of statistics, a lot of time we calculate the sample and not as a whole, as a mass, right? So that's why we focus in a lot in type 1 error, because the individual, the innocent guy go to jail. That's where is important to the individual, right? But again, we try to make it small, but the problem is if we make the alpha small, the smaller we make the alpha, the larger the beta, which is the beta is the probability of type 2 error happen. So we try to kind of balance them out, which is we kind of just level them out in terms of the 5%, which is the same as the cutoff of the unusual item. Okay, so again, just know that the alpha, the level significant that we calculate is the probability of type 1 error. So we try to limit the probability of type 1 error. We limit when the item is true, but we reject it. Okay, we try to limit that. Okay, the last thing we have is the p-value. The p-value, you know, sometimes you might not, I mean, if you have to write a report, you know, if you have to write a report, then you probably want to put this p-value in. The p-value is basically tell you how significant, how statistically significant are we, right? If you look at this thing here, the p-value is 0.049 versus the p-value of 0.0001. Remember, the smaller, both of them, we reject H0. But how confident are you when you reject H0? Because again, if the smaller the p-value, the better we are, because the smaller the p-value, the more chance that we know that type 1 error does not occur, right? So that's why we say the smaller the p-value, the more significant we have. Because both of them we reject, but looking at this thing here, we still have very close to the boundary of 0.05, which is we are not that statistically significant, right? Because it's still close to our cutoff line, right? But if it's further away, like 0.0001, which is very humongously small compared to this one, then we say that is significant, right? Right? Statistically significantly small. So we have more confidence that type 1 error won't occur. Okay. So again, this is just something that you want to, you know, for your information between the interval, the confidence interval versus hypothesis testing, and again your alpha, and vice versa, the p-value, why the p-value is important if you want to include the p-value. Okay. So let's take a look at chapter 8 section 8.3, which is, as you can see, all we doing is the same, which is hypothesis testing for a population mean. We're still testing the population mean, but the population standard deviation is unknown, right? The population standard deviation is unknown. So which is, this thing here is very related to that 7.3 or 7.2, right? So we begin this, let's go straight to the problem, right? We began this section with this example. Suppose that in a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss were X bar equal to 2.2 kilogram, with the standard deviation of S equal to 6.1. Can you conclude that the mean weight loss is greater than 0? So looking at this thing here, hopefully you guys identify the difference, right? If I give you two problems side by side, hopefully you identify the difference, or this is your objective that you need, right? You need to identify that one thing different is they tell you that the sample standard deviation, right? This is the difference, ladies and gentlemen, between 8.2 versus 8.3. 8.2, they give you the population, they give you the sigma. 8.3, they give you the S, which is the sample standard deviation. So because it's a sample standard deviation, hopefully you remember that we have to use the t distribution, which is now the only thing different is, guys, step 3, instead of plugging into this calculator, the Z calculator, the Z confidence interval, we have to plug into the T test statistic. And again, the T test statistic, we have to use the T critical value. And to find the T critical value, you need the degree of freedom, which is the degree of freedom is n-1. Okay, so the only thing different now is instead of using the Z critical value, the Z distribution, the Z test, we're using the T critical value, the T distribution, and the T test. Okay, so again, look at this thing here. Let's go over, for this particular problem here, just do what we did earlier, right? The previous problem, again, I just used the same problem. If you were to do what you do earlier, which is, again, we just circle all the number we have, right? Circle all the number we have and ask ourselves what number is important, what number is useless, and what number can we distinguish one or which one. So looking at this thing here, hopefully you guys see that, 12 is useless, right? That is just a information or a category or time frame, right? So the 12 here, the 12th month, we don't worry about the 12th month. So hopefully looking at this thing here, just like before, we have to extract out our information, right? Our data. So clearly, I hope you guys see clearly that the N, how many subject we have, how many total item we have, which is in this case, the total item N is equal to 76. And again, they give us an X bar. Clearly, they give us X bar, which is the sample mean. And then they give us the S, which is the sample standard deviation. And again, they give us the alpha, which is, again, hopefully you guys see that this 4 item is the easiest 4 item to spot out, right? They give you the symbol, so if they give you a symbol, there's nothing to spot out, right? Just extract them out. So now, what do they ask us to do? Well, they asked us, can we conclude that the mean weight loss is greater than 0? So what is this 0? Well, this 0, do you agree that this 0 is kind of like a focus point, right? We want to know if the number of people weight loss, they in this program, do they lose more than 0 pound, right? Or they just break even, right? So this 0 is the specific number that we try to compute, we try to test, right? And that is what I told you guys, that most of the time, the specific number that we're looking for is in the question itself. In the can you verify, can you conclude, can you state, whatever they try you to prove, most of the time, the specific number, the specific value is in that statement, in that sentence. So if we know the specific value, the same as before, the first step is we need to state the hypothesis test. And to state the hypothesis test, we need to know the specific value. And if we know the specific value, your H sub 0, your dummy hypothesis will always be equal to, which is the mu is equal to 0, equal to that specific value. And then what is your H sub 1? Hopefully you say, oh, we need to know if it's greater than. And why is this important? Because if we test for greater than, we know that this is the right tail test. Okay. Remember, the previous one is not equal to, that's why we have a 2 tail. This one here is greater than, so we have a right tail test. And now we need to find a critical value. Like I mentioned to you guys, because they give us a sample, again, because they give us a sample standard deviation, ladies and gentlemen, sample standard deviation, we have to use a T critical value and a T item, which is, again, looking at this thing here. Looking at this thing here, let me share you my screen. So this is your table A, appendix A3. which is the same table before, which is reminder that this is your T critical value. Your T critical value is all of this number here. Last time, what did we do? Last time in chapter 7, we're looking for a confidence level, which is the confidence level is down here. And then we just say, okay, if the confidence level is 95, whatever my degree of freedom is, those are my T critical value. Now, the difference between this item now is, instead of look on the bottom for your critical, for your confidence level, your alpha, ladies and gentlemen, your alpha is right here. They give you this alpha right here, which is again 0.01 or 0.1, 0.05, 0.025, 0.01, so on and so forth. This is your level of alpha. So to utilize this table, this is my alpha. So the alpha that they give me is 0.05, which is, I'm looking at this column. My column is 1, 2, 3, 4. So again, this is the column I'm looking for my alpha of 0.5, which is right here. So now what do I need to do? Which is, again, I need the degree of freedom. If you remember, your degree of freedom is 76 minus 1, which is 75. And again, we don't have a 75, so we used a 61 less, which is right here. Okay. But again, I will go back to this item a little bit. But if you were to want to utilize this thing here, ladies and gentlemen, remember yesterday I give you the common value. The common value I give you guys yesterday in terms of the alpha for the Z critical value. The Z critical value is right here, which is if the alpha is 0.05, remember if it's left tail is 1.645, if the right tail is if it's left tail is negative, if the right tail is positive. So the Z value is still right here. It's just that now instead of look at the confidence level, you have to look at your alpha, depending on what alpha they give you. So the confidence level is on the bottom, the alpha item is on the top. Okay, so again, that is what we have in the sense of that. So let's go back to this particular problem. And again, like I mentioned to you guys, because they give us a sample standard deviation, we use the T distribution and the T critical value. And in order for you to find a T critical value, you need that degree of freedom. And for us, the degree of freedom is 76 minus 1, which is 75. And if you remember to look at the chart, we don't have the actual 75. The rule is, if we don't have an actual 75 as in your degree of freedom, then you have to use one less, which is reminder, this is what we have right here. Again, this is my alpha 0.05, right? And I have to go from that line, I have to go down to my 76. But again, my 76, I don't have a 76. I have to use one less, which is the one less is the 60, which is my alpha is 0.5 and my critical value is 1.671. Okay, and that's where the 1.671 come from, which is reminder we have to use that T distribution, T critical value, which is we need the degree of freedom. So that's where my critical value come from. Okay, and we deal with the T, so all the numbers inside that table, not on the bottom. Okay, so now once we find a critical value, what do we do? Well, this critical value tell us a few things, which is tell us that is my boundary. And because I know that it's a right tail test, which is now is tell me that this is my critical region, which is if the T test is fall under this region, is a reject region. If it's fall on the left, it will be a fail to reject or do not reject region. So now what do I need to do? Which is again, as you can see, hopefully you guys see that is the procedure is the same as before. State your hypothesis, find a critical value, find, sketch your normal distribution graph, and then tell yourself what is your critical region and the reject region and do not reject region. So now I will skip the formula, which is now, as you will see, or as you saw yesterday, we can use our calculator to calculate this thing here, which is your calculator, instead of using the Z test, as we mentioned, you hit stat, and you go over to test, which is the second option, your t-test. That is what we want to choose, which is the t-test. And again, make sure that the input is under the stat, because we have the stat data, not the regular data, the raw data. So again, your stat, this is what you need. You need your mu, which is your mu sub 0 is 0. You need the x bar, which is in this case 2.2, is your sample mean. You need the sample standard deviation, which is in this case 6.1. And then you need the n, which is in this case we have 76. And again, what kind of test do we have? We have a right tail test, so I'm choosing a right tail test, and then I calculate. So again, those are the same information that you needed from the previous 8.2. It's just that now, instead of the population standard deviation, we are using a sample standard deviation, which is the two output that we're looking for is the t, which is the t is your t-test statistic number, which is 3.144, and the p-value is 0.0011 or 0.0012. So again, those are the two numbers we extract out, which is, again, we have the p-value 0.0012. And again, why do we extract out the p-value? Because if you remember, the p-value tells us that if the p-value is smaller than alpha, we will reject H sub 0. Or if you use the critical value method, this is my boundary, and this is my reject region, this is my fail to reject region. And again, 3.144 is somewhere over here, right? 3.144 is somewhere over here, which is under my reject region, which is what is the result here? The result is we reject H sub 0. And if we reject H sub 0, if we throw away H sub 0, we say that we do have enough information, or we have enough information, we have enough evidence that the mean weight loss is greater than 0, right? I mean, if it's not greater than 0, you defeat the purpose of this diet, right? 0 is meaning you in this diet and you break even, you don't gain and you don't lose, right? 0 weight, right? So so we try to see if this diet work, right? Which is, we just want to know if you lose more than 0 pounds, which is you lose something, then the diet work, right? So again, based on this information, this is what we have, and based on this information, this is what we ask you, in the sense of hypothesis testing. Okay, so hopefully you guys see that it's the same as yesterday. Everything is the same except that instead of a t critical value, yesterday we used the z, today we use the t. And how do we know we're using the t? Because we have a sample standard deviation, or as you will see later, the lack of the standard deviation. Okay, so if they give us the population standard deviation, the z. If they give us the sample standard deviation, the t, just like chapter 7. Before we get to the next problem, question with this one here, ladies and gentlemen. All right, let's take a look at the next example here. So looking at this thing here, let's take a look at this item, which is, again, if you look at, one thing is, a lot of students, when I tell them, just go in and ask what they ask you to calculate. Sometimes the information, you read the information and you lose track of what you need to do, right? They ask you, can you conclude that the mean tuition and fee for the private institution in California is different from 35,000? So we want to test if it's different, which is, if it's different, meaning not the same, meaning it's not equal to two-tailed test, right? So again, looking at this thing here, we know that we need to do part A, state the null and alternative, calculate the t statistic test, how many degree freedom we have, and then state your conclusion, right? So if you know, and for those of you who don't know how to start or where to start, again, just go in and just circle the number, like how many number, what number do they give me, and what is that number after, right? So again, if you go into this problem, I don't read the problem. I just go in and I know that I have, if you go in, you say, okay, 14 private college, 30,000, 37,900, 7,200, and 35 37,000, which is, again, looking at that, those are all the number I have, right? So now what is this 14? Hopefully you guys see, well, the 14 is the sample, right? So the sample, which is the n is equals 14. And again, what is the 37,900, which is, again, they say that the mean for this sample, which is the mean, which is, again, hopefully you see that with this 14 private college, the mean of this 14 is 37,900. With the standard deviation, which is the standard deviation is the sample, right? I told you guys this last time, is with the standard deviation, unless they spell it out, population standard deviation, or they give you the sigma, then this standard deviation is the sample, the S, right? So again, we have this mean for this sample come along with the standard deviation, which is the sample standard deviation. So again, out of the 4 number, I have 3 of them, right? They don't give me the letter alpha down here. They give me the alpha, which is, I have that alpha down here. But now the only thing left is the 35,000. What is this 35,000? Again, that is the number that you want to test. You know, that's like just